Hello everyone, welcome back to my channel. Today we're going to be starting the dynamic programming series. And today we'd just like to talk about what dynamic programming is generally. So dynamic programming, called DP. The idea here is we if you think about it, it's just like a way to do exhaustive search and then do this exhaustive search in a smart way. And this is basically what dynamic programming is all about. The question now is, what does it mean? We know generally when we say exhaustive search is usually bad. Yeah, exhaustive search. So an example would be a brute force approach to find all the pairs. Yeah, some of all the pairs of numbers in an array. Yeah, so using brute force, say that we have like these pairs of elements in an array. Using brute force, we could do any combination, pick every I and then pick every j, and then combine. Um, that will be n squared. Yeah, but with dynamic programming, problem is usually worse. Yeah, so say that give you an example, tell you that you should figure out say we have this, we have maybe 6, maybe 9, maybe 3, 11. We tell you find the maximum sum of non-adjacent numbers in this entry. So what that means is that you could pick 2 and then sum it with 4. Pick 4, sum it with 6, pick 6, sum it with 3. Yeah, and then determine what sum is this. This is 15. There's one way you could pick it, and the other way you could pick is you could pick 2, then jump to 5, then from 5 pick 9, from 9 pick 11. So in that case now we have it's 20 and that's 27. Do you see? So that's one way we could do it. So the other way we could do it is try to be exhaustive. Yeah, and then see if we can pick 2 and then decide on if we need to pick 4 next, or we need to pick 5 next, or we need to pick 6 next. Yeah, and then once we are done picking from that 4 again, we determine if we need to pick 6 next, like that. We could have started from 3 and then decide if we need to pick 5 next or pick 6 next. Yeah, so that will be exhaustive search. And then if you think about it, the options we have here is a lot. Yeah, so you could either start with 2, then go with 4, or go with all the other options. So basically, it could be like for every option we have, for every entry we have in the array, for each of the n, we could then decide to pick up any of the other n elements. You see, so this is roughly the time complexity. You can see that this is exponential to the value of the size of the entry in the array, in addition to being raised to the value of the size of n. This is really bad. Yeah, so but rather than do this, that's where dynamic programming comes in. It's also going to be a form of exhaustive search, but we're going to be smart about the way we search. Right, so how do we do this? Here's the thing. For the online programming kind of problems, there are two very important properties that the question needs to have. Yeah, or rather two very important properties that either the question needs to have, or we can model the question in such a way that it now has those properties. Yeah, so those properties are the fact that the question or a solution to the question needs to be needs to have an optimal substructure. And the second one is the sub problems should be overlapping. So we say overlapping sub problems. All right. So what do this mean? Because it really doesn't make sense. So the first part, optimal structure. So what that means is, let's use a simple example. Let's use the Fibonacci numbers. We know that the Fibonacci numbers is a sequence that starts from 0, 1, Then the next is 1, then we have 2, then we have 3, then we have 5, then we have 8, then we have 13, then we have 21. Yeah, so this this is the Fibonacci series. And basically the how you generate these numbers is, you start with 0 and 1, and then for every subsequent number, that value is the sum of the two previous numbers. So this one is the sum of this and this. Here we get, yeah, 2 is the sum of this and this, 3 is the sum of this and this. So if we index all of these entries, this will be index 0, index 1, index 2, 3, 4, 5, 6, 7, 8. And what we just said now is the fib of this fib of 2 is equal to the fib of 1 plus the fib of 0. So what that means is, for any hypothetical n, fib of n, it can be expressed as fib of n minus 1 plus fib of n minus 2. Yeah, and very important point, I mean, n has to be greater than or equal to 2. Yeah, so n is equal to n is equal to n is greater than or equal to 2, and fib of 0 is 0, fib of 1 is 1. Yeah, so hypothetically speaking, so let's say now you have this definition, and then you are actually you have this definition of, if I'm the Fibonacci number of a particular number n is equal to Fibonacci number of the number before, and then the number before that, and then you have these cases, and then you have to now figure out what is the fib of a particular number. A particular number, it could be like 23. Figure out fib of 23. So the way you do that is, you need to identify that this problem has an optimal substructure. So what that means is, we can divide this problem into subproblems. So for example, fib of n can be divided into sum of fib of n minus 1 and fib of n minus 2. These are subproblems. So to solve this one, we need to solve the subproblems, first one and the second one. This is a subproblem. This is another subproblem. Yeah, so that's what subproblem means. And then the next is the fact that we're going to sum these two subproblems to form this one. That's so the fact that we can sum the two subproblems together to get the solution to the larger problem. We need to sum fib of n minus 1 and fib of n minus 2 to get fib of n. Means that this problem has an optimal substructure. Does that make sense? So the subproblems that can be added together to form the solution to the larger problem. That is what we mean by optimal substructure. Yeah. So the second one, overlapping subproblems. So now, when it comes to overlapping subproblems, what that means is that, so hypothetically speaking, assuming that we need to figure out the fib of 6. Yeah. So what we'll do is, okay, we need to figure out fib of 6. We would say fib of 6 is, fib of 6 is fib of 5 plus fib of 4. Yeah, but we need to solve for before 5. We don't know what fib of 5 is, so we need to solve for fib of 5 first. Fib of 5 is fib of 4 plus fib of 3. We need to solve for fib of 4 too, so we need to say fib of 4 is equal to fib of 3 plus fib of 2. Then we need to solve for fib of 2. Fib of 2 is equal to fib of 1 plus fib of 0. And so we know this, so we know fib of 2. Yeah, so now once we are done solving all of this, all the way, then we would have known the solution to fib of 4. Then once we have that part done, we now need to solve for fib of 3. Yeah, so fib of 3 will be fib of 2 plus fib of 1. Then fib of 2 will be fib of 1 plus fib of 0. So once we have that, we now have the solution for fib of 3 and fib of 4. We sum together, we get the solution for fib of 5. This way would have been done with solving for fib of 5. Then we need to solve for fib of 4, which will now be, fib of 3 plus fib of 2. Yeah. So the important point here now is, if we notice something about these problems now, is in trying to solve for fib of 6, we need to break it down into 2, 5 and 4. So for 5, we break it down into 2, 4 and 3. Then to solve for 4, we break it down into 2 again, 3 and 2, until we get to this 1 and 0. Now the problem is, in solving for 5 and 4, in solving for 5, we need to break it down into 4 and 3, such that we took one part to first solve for fib of 4, then we now come back to solve for fib of 5, for fib of 3, and then we now go down the path again. But do we notice that somewhere along this path, instead of attempting to solve for fib of 3, we see that we solved for fib of 3 at some point before? Yeah, actually I skipped that here, so it should have been fib of 3 here, which would have been fib of 2 plus fib of 1. So that way we'll have solved for fib of 3 here. Do we see? So, and on the other part, trying to solve for fib of 4, on this other part here, you see that this one has already been solved here previously. Yeah, so the fact that in trying to solve for one part, we could have seen the solution to another problem that we need. So instead of solving this fib of 4 multiple times now, in this case, this is twice actually. This case is twice. But for fib of 3, we solve it a couple of times. So 1 here, 2, 2 here, and 3 here. So 1, 2, 3. And 3 times we will keep attempting to solve for fib of 3. And for lower numbers, most likely. So imagine now we have like a fib of 20. Can you imagine how many times we'll be repeating problems? Yeah, so this is the idea behind overlapping subproblems. So we have subproblems in the process of solving for fib of 6. We have like different subproblems. Yeah, and in these subproblems, they overlap somehow, such that we do not need to recompute them over and over again. If a question or the solution to a question can be modeled this way, that means that you can apply dynamic programming to it. Yeah, so those are the key requirements, understanding what dynamic programming is and what it's about. All that is left is just attempting to solve problems. So we'll see you guys in the next video, where we'll be talking about the first dynamic programming pattern, which is the Fibonacci numbers pattern. Don't forget to like, share, and subscribe. See you guys once again. Bye.